All right, so this is homework 1, part B, part 1. By integrating the pressure forces on a cylindrical container, derive an expression relating to the minimum wall thickness necessary to the pressure, height, radius, and tensile strength of the wall material. So first I'm going to draw out the situation a little bit. So we have a cylinder. That's a great cylinder with height h, and then top down view. So we need to try to find the force first. So we know that force is related to area and tensile strength. So we're going to do F equals tensile strength times our area. And our area in this one will be like half of the cylinder. Like if you cut it in half. So it'll be 2 because it's the thickness. So 2 times the thickness times the height. And that'll be the area of the cylinder. So now we need to find an equation for pressure. So that'll be P times dA. And so pressure will stay the same. We take this step further, and it's an integral. So pressure, and so we have the height of the cylinder times the radius, and then so from the center we need this length right here. So we have the radius, and this will be d theta. So pressure times height times radius times d theta. And then we also know our bounds of the integral. And since it's only half, I should have drawn these like this. So we from the top to the bottom, or from negative pi over 2 to pi over 2. We're also missing one more thing. So this would just be if we took like a chunk of the circle at a time. But instead what we want to do is we want to have them all going in the same direction. So what we're going to do is we're going to add a cosine theta, because that'll be this angle. So if you multiply the radius times cosine theta, that'll get, or the pressure times the cosine theta, that'll get it all in the x direction, and they'll all be the same. So we're also going to add cos theta, kind of like that's there. Okay, so now we're going to evaluate the integral. So we're going to have P H R times sine of theta evaluated from negative pi, bad pi over 2 to pi over 2. So when you evaluate that, you'll get 2phr, and that's obviously equal to the force. So what we can do is we can plug this into this equation, then we get 2phr equals tensile strength 2th, and then we're going to solve this for the thickness. So these will cancel out. So then we'll get T equals 2 pressure times radius all over tensile strength times 2. And that is how you do that. Okay, so this is homework 1, part B, part 2. So first one, we need to repeat B1 for a spherical tank, again relating to the minimum wall thickness. to the pressure, radius, and tensile strength. So first, I'm going to draw the situation. So this is a 3D shape. This is a 3D shape, so it needs to be a 3D plane. So you have our X plane, make this a little longer, Y, and Z, and as a sphere. So we have our little bit of area, a little bit of curve. That's going to be dA. And then the center of the sphere is the origin of the grid. This angle is going to be d theta. This length is going to be r times d theta. And then this is going to be theta, this angle. So we'll project that down to the xy plane. Again, coming from the origin. And this angle is phi. This is going to be d theta, or d phi. This length is going to be r times cosine phi. And so like this the cylinder, we know that the force is equal to the area times the shear stress. So the force is equal to the shear stress. And like this one, it's 2 times the area. So the area is 2 times pi times the radius times the height times the thickness. So now we're going to move on to dA. So this is going to be r squared times cosine theta times d theta times d phi. Okay, so then we have EF. And this is just going to be P times dA. And then we have dFx, which is equal to be dF times cosine theta times cos of phi. So then we can put the df into dfx. So then we get f of x equals, so this is going to be df, so we have to put in these two equations. So pressure times r squared times cosine squared theta, because there are 2 cosine thetas, and times cos phi times d theta times d phi. So I went to a new page to give myself some more space. One mistake I made was that this is still dfx actually, the same equation, but now we can start integrating and that will make it just fx. So still pressure times radius squared and the integral of cosine squared theta. And the limits of this integral are from negative pi over 2 to pi over 2. this other integral, same limits, negative pi over 2 to pi over 2. Forgot d theta. This is cosine of phi times d phi. And so if you evaluate this integral on the right side, this would just come out to 2 for this one. So now we need to focus on this integral, cosine squared. So first, I'm going to rewrite it as cosine theta times cosine theta. So cosine theta times cosine theta, d theta. So what we need to do is we need to do integration by parts. So u would just be cos theta dv is cosine theta d theta. Du would be negative sine theta. And then v would just be sine theta. So now we can rewrite this. So we cosine theta times sine theta. And then you can evaluate that. So let me, the other integral should be sine pi over 2. This should just be sine squared. So what we can do now is we can evaluate this one because this one will just come out to 0, so we can get rid of this. But this one, we're gonna have to rewrite this one actually, so I'm gonna go ahead and erase part of it. Erase this part. And move this over here. So we're actually gonna rewrite this as 1 minus cosine squared. That's a 2. Cosine squared theta d theta. So what we can do with this is this originally comes from this integral right here. So what we can do is move this to the other side. So we get 2 cosine squared theta d theta, and this is just 1. So now I'm going to rewrite the whole thing so it's more clear. So I'll do this here actually. Okay, so that equals the integral this would just be 1, and then this would be 2 times the integral. So if we evaluate this, we would get pi. So we get 2 of this integral equals pi. So what we'd have to do is divide both sides by 2, and you get pi over 2. So this integral is equal to pi over 2. So now, since we know that this integral is 2 and this integral is pi over 2, we can rewrite f of x. So fx equals pressure times radius squared times pi over 2 times 2. So these will cancel out. So you get f of x equals pressure times radius squared times pi. So now what we can do is we can set these two equations equal to each other and then solve for the thickness. So go ahead and move this out of the way. So pressure times radius squared times pi equals shear stress times 2 times pi times radius times height times t. So let's divide this side by this side, and then we'll get t equals p or r squared. This will cancel out over shear stress times 2 times r times h. You can cancel one of these out. So equals p over RH. And 2RH times 2. All right, so this is homework 1, part B, part 3. So for this one, to explain how the results in parts B1 and B2 can be obtained through judicious choice of a dividing plane through the cylindrical and spherical tanks. So for this one, I'm going to draw it again. So we have a cylinder. I'm going to redraw that. And then our top-down view. So there's a gas inside of this the cylinder, right? And so we can see is that all of the force exerted by the gas or whatever inside it goes this way. But since it's not accelerating, there must also be a force going the opposite direction. And this is true for every direction around. So what we can do is we can take the area of like the middle, which is basically just a rectangle, and we can use that to find the force exerted. So the force is equal to 2 times the radius or the diameter times the height, since it's a cylinder, and then obviously the pressure there. And then we do that and we get the force is equal to 2 times PHR, which is the same thing that we got for when we integrated in the first part. And we can see that it was much easier just to do it this way.